Hello everybody, and welcome back to another quiz tutorial. In this tutorial, we're going to be covering quiz number 16, which is the Cauchy stress tensor. So last week we finished up strains and we talked about the green strain matrix and the small strain matrix. And now we're taking it a step further and discussing stresses, because of course when you guys think of strains, you guys think of stresses or vice versa. So the goal of this week is to figure out, okay, well how exactly does the stress tensor work? What are some properties of it, etc., etc. Because after that, we can start to create some relationships between the stress tensor and the strain tensor, because of course that's what we want. If we know the stresses, well, what are the strains? Or if we know the strains, what exactly are the stresses? So before we jump into the theory, I just wanted to apologize for the quiz last week. I know it was extremely long, and with a long quiz comes video editing, and my video editing was complete dog shit. And I'm really sorry about that, guys. Unfortunately, this quiz is also a really long quiz, so I might have to do some video editing, and if I do, as you guys will see, it's probably also just a nightmare. So if that happens in this quiz, I also apologize for this quiz, as well as what happened last quiz. So with that being said, and the disclaimer out of the way, let's jump into the theory. So as you guys will remember, I had that nice picture of the little imposter characters to try and show you guys how exactly strain works. Now, stress is a bit easier because all we have to do for 2 dimensions is just take a stress block and label all the stresses that we can see on there. And from here, if we look at the stress block, we can say, okay, well, this is just a nice matrix, which is 2 by 2, and it's as follows. So in the horizontal direction, those normal stresses, well, those are sigma 1, 1. In the vertical direction, so that x2 direction, well, those would be sigma 2, 2. And of course, the off-diagonal components, that's sigma 1, 2 and sigma 2, 1, those are the shears. So I look at kind of the shears on each one of the faces. Now for 3D, it gets a little bit more complex, a little bit more faces to consider, but in essence we can do the same process as above to create the following stress matrix. So right now it's not even really a stress matrix. If we look at it, it's just a bunch of sigmas. Now, the key to the Cauchy stress matrix, which you guys will also remember from the strain matrix, is that it's actually symmetric. So if we look at these two matrices above, they can be simplified as so. So if we look in the 2D stress matrix, we have sigma 1 and sigma 2, 2, and then we have a sigma 1, 2, and that's it, because sigma 2, 1 is the same as sigma 1, 2, so in total there's going to be 3 unknowns. Now if we look at the 3D case, we have a lot more simplification, where we'll have sigma 1, 1, sigma 2, 2, and sigma 3, 3, which will be in our normal directions, and then we'll have sigma 1, 2, sigma 1, 3, and sigma 2, 3, which will be the shears in each one of those planes. So it's actually pretty simple, but now the question is, well, what exactly can we do with this matrix? Well, we talk about internal stresses. So this is going to be kind of the first thing. You guys may not know it now, but internal stresses are the key to actual simulations. When we're running simulations and we're doing those numerical analysis, we use internal stresses to kind of figure out if the section is in equilibrium. And if it is in equilibrium, then that's perfect. There's our solution. But if not, then we're going to have to make an iteration and kind of repeat calculations. So the best way to describe this is, remember statics? When we had a nice long beam and the question was always, determine the shear, determine the bending moment, stuff like that. Well, we're kind of going to do the exact same thing, except for a stress element. So if I look below, I drew a nice big rectangle and I drew it kind of like a beam. So you guys will go, oh, this looks like Eng 130. Well, although it looks like Eng 130, this is a stress element. So in actuality, this would be a very tiny little piece. This is not a big long beam. It's just a tiny little piece. And what we can do is we can say that this stress element is a point on our body. And what we can do is we can cut open that stress element as follows. And inside of there, we know that there's going to be internal forces. So what happens is we're going to have 2 major vectors that we're going to have to keep track of. The first one is I call the normal vector n, which is a normalized vector perpendicular to the cut plane. So the first major key here that you guys are always going to have to remember is this vector n is going to be normalized. So if there's an exam type scenario and they give you n, but it's not a normalized vector, you guys are going to have to normalize it before you carry forward. It's a perfect trap because a lot of students will say, okay, well, there's my vector, I'm just going to proceed. No, that's a trap. Please be careful, this vector is normalized. And the reason why we use this vector n is to define our cutting plane. So as you guys see here, I have a plane that I cut and it's on an angle, but the question becomes, well, what angle is it? Well, it's actually going to be very important what angle is it, because whatever angle we choose or whatever our cutting plane is, it will impact the results. So that's why we use this vector n, which is perpendicular to our cutting plane, because it defines the direction, and from there we can carry forward into the second vector, which is called the traction vector. So in this course, we call it the traction vector. If you guys look in textbooks, it's sometimes called the stress vectors. So these are all the internal forces. And as you guys can see, it's just a random vector, and it represents, again, the internal stresses. Sorry, I said internal forces is the internal stresses. So using this n, we can find the traction vector Tn. But then the question becomes, okay, well, how exactly do I get that traction vector? So if I look at my current states, I know I have my vector n, which is normal to the cutting plane, and I have a traction vector Tn, which is those internal stresses. But how exactly do I find those internal stresses? Well, using linear algebra, there's actually a very nice formula where our traction vector n is equal to our stress tensor. So that sigma right there, that's a tensor or a matrix multiplied by our normal vector n. So usually in these kind of problems, we're given the stress matrix and we'll be given our normal vector n. All we have to do is multiply them together, and that'll give us our traction vector. Now, again, the key to remember is that n has to be normalized. If you guys don't normalize it, you guys will get the traction vector wrong, and you guys will get everything else wrong. So it's not a happy day in case you guys forget to normalize n. But what else can we actually achieve using this traction vector? Well, the first thing is the normal stress. So this is the stress that goes in the direction of n. So if I were to cut this face, then the stress pointing perpendicular to this plane, well, that'll be our normal stress n. And if we look at n, it's a very simple formula. All we do is we take our traction vector and we dot it. So that right there, that's a dot product. That is not multiplication. And we dot it with our normal vector n. So again, the formula is, again, very simple. And now we say, okay, well, of course we have normal stress, but we also talk a lot about shear stress. So is there a way to get the shear stress? Well, yes, there is. So the shear stress, which is denoted as tau, is simply the norm of vector Tn minus sigma n, so that's the normal stress, times n. And if we look at our diagram below, we can see that the normal stress and the shear stress are perpendicular to each other. So there's another kind of key piece of information. We also see that the normal stress vector plus the shear stress vector is equal to the traction vector. So again, there's a nice little fun fact too. But now before we begin, I just want to actually start talking about what to expect, because we have a Tn, we have a tau, and we have a sigma n, and it's very easy to start getting these mixed up. So let's look at the traction vector really quick, Tn, and look at what's going on. Well, we take a stress matrix and we're multiplying this by a vector. And if we do that, well, then we know that that Tn must also be a vector. So here's the key here, is I'm going to show you guys what exactly these are supposed to be so there's no confusion. Now, if we move down to the normal stress, that's sigma n, this is equal to a vector Tn dot with another vector, the normal vector. And we recall that if we do a dot product, this will give us a scalar value. So of course, when you guys find the normal stress, this should just be a single value. It should not be a vector. Now the shear stress, again, we're taking a vector and we're minusing another vector, so that'll give us a vector. But then we're taking the norm of that vector. And of course, the norm of a vector, well, again, that's also just going to be a scalar. So these are things to look out for. I know a lot of students will say, I got my shear stress as a single number, but shouldn't it be a vector? No, our shear stress should actually just be a single number. So this is why I'm showing this in there, just to really show you guys what to expect. Now, the final thing that we're going to discuss before you actually move into the quiz is principal stresses. So principal stresses, hey, Clayton, I remember principal strains. Are they similar? Well, the answer is yes. The term principal, as you guys will see, will always refer to a very specific kind of phenomenon. Now, normal stresses, which are denoted as sigma 1 and sigma 2, and shear stresses, which are sigma 1, 2, are dependent on the element orientation. So if I were to take my stress element in its current state, we have something like this, where we have, of course, sigma 1, 1, sigma 2, and we have a shear stress sigma 1, 2. Now, if I were to take that element and say, okay, well, instead of its current state, let's rotate it. I can get a state like this, where I'll have sigma prime 1, 1 and sigma prime 2, 2. But wait, there's no shear stress. So if I look at this and say, okay, this is interesting, I can conclude that there is an orientation in which my shear stress, sigma 1, 2, is 0. So the question becomes where exactly do I get this orientation from? Well, let's look at the stress matrices of both of these elements. So I look at the first one, where I have sigma 1, 1, sigma 2, 2, and sigma 1, 2. It's just my standard Cauchy stress matrix. Nothing special. But after I transform it, I realize, okay, well now, after I transform it, my shear stress is equal to 0, so therefore sigma 1, 2 is equal to 0, and I get this, where sigma prime is equal to sigma 1, 1 prime and sigma 2, 2 prime. And you're thinking, oh wait, that looks very, very special. Well, you're right, because when the shear stress is 0, the stress matrix is diagonal. Wait a second, diagonal matrices, I've seen that before. Well, of course, that's what happens when we find the eigenvalues. So therefore, this stress matrix here, that's sigma 1, 1 prime and sigma 2, 2 prime, those are actually the eigenvalues of our stress matrix, sigma. And what we say is those two eigenvalues, the sigma 1, 1 prime and the sigma 2, 2 prime, we call those our principal stresses. And of course, associated with eigenvalues are eigenvectors. So the coordinate transformation matrix Q consists of the eigenvectors of the stress matrix sigma. And what we also call those eigenvectors are the principal stress directions. So of course, eigenvalues denote directions, while the eigenvalues are actual values. So that's it for kind of the theory roundup. I hope you guys kind of are on the same page. Again, this is going to be a long video because the quiz is pretty beefy, but I find that if you guys really understand what's happening here, then the rest of the stress kind of portion of the course will go by really smooth. So again, I hope you guys understand. But with that said, let's jump into the examples so you guys can see these terms in action. All right, so as mentioned, the quiz is pretty beefy, so grab your popcorn, grab your pops, settle in, get comfy, because we might be here for a little while. I'm going to try and do it better than last quiz. I know I didn't do a very good job with time management, but I'll try better this quiz. But hopefully it goes well and you guys are happy by the end of it. So the first question is actually really simple, and says categorize the following 2D stress states into general, principal, and hydrostatic. So before we begin, let's just discuss, okay, what are each of these stress states? So the general stress state, I'm going to come down here and I'm going to put general. This is a stress state in which tau, which is our sigma 1, 2 in this case, so our shear stresses do not equal 0. They can be any number. And this one's the very easiest because all we have to do is look at the tau, the stress, sigma 1, 2, and see if it's equal to 0. If it's not equal to 0, we can say that this is the general stress state. And I'm going to put a G here for this so I don't have to write down general all the time. Now the second one, which is the principal, so prince, and I can't even spell. I kept spelling this wrong all the time, so I had to learn. So the principal stress state is when tau, which is equal to, again, sigma 1, 2, our shear stresses, they're equal to 0. So there's the first contradiction between the principal and the general stress state. Now, if I go down here to hydrostatic, which I'm going to go hydrostatic, this is also when tau, which again is sigma 1, 2, is equal to 0. So what's the difference between the principal and the hydrostatic stress state? Well, this has to do with our normal components. So in the principal stress state, sigma 1, 1 will not equal sigma 2, 2. However, in the hydrostatic stress state, our sigma 1, 1 is equal to sigma 2, 2. So there's the key difference between them. So for the principal, I'm going to put P, and then for the hydrostatic, I'm just going to put HS. So here's kind of the criteria for each one of them, and all we have to do is go down and see these matrices, and we can make our conclusions. And now really quick, before we begin, I just want to talk about the hydrostatic stress state. And you guys say, Clayton, well, what's an example of hydrostatic stress? I can't talk. Oh my gosh. The hydrostatic stress state. Well, there's two good ones that come to mind, and that'll be something underwater, because of course the pressure due to the water is the same on all faces, or something buried underneath the soil. So of course, pressure from the soil is the same on all the faces. So we're going to come down here. We're going to look at the first one. So again, the easiest way to try and start these off is look at the shear stress. In this case, I have shear stress at 2. So in this case, my tau does not equal 0. Therefore, this is going to be a general stress state. Come down to the second one. Oh, again, my shear stress does not equal 0. So I can say that tau does not equal 0. Therefore, this one is also a general stress state. So if you guys remember those criteria, once we get going, it's actually fairly quick. Come down to the next batch. Again, I look at tau. So, oh, this time tau is equal to 0. So therefore, it's going to be principal or hydrostatic. So then I look at sigma 1, 1 and sigma 2, 2. I got 1 and I got 3. So in this case, sigma 1, 1 does not equal sigma 2, 2. Therefore, this would be a principal stress state. If it was hydrostatic, then sigma 1, 1 would equal sigma 2, 2. I come down to the next one. Oh, 0 and 0 for my tau. So I can say, okay, well, tau is equal to 0. So it's going to be principal or hydrostatic. So I look at sigma 1, 1 and sigma 2, 2. Well, I got -1 and -3. So in this case, sigma 1, 1 does not equal sigma 2, 2. Therefore, this is also a principal stress state. So just like that, already halfway done the question. Let's go on to the next two. Again, I can see I got 0 shear, so my tau is equal to 0. So it's going to be principal or hydrostatic. So I look at sigma 1, 1, sigma 2, 2. Well, I got an eraser by accident. I got 1 and I have 0. So therefore, sigma 1, 1 does not equal sigma 2, 2. Therefore, this again is also a principal stress state. So a lot of principal stress. I don't know why I say stress as stress. Oh my gosh. All right. I'm sorry about that, guys. All right, moving on. The next one, F. We have 0 and 0 for our shear. So our tau is equal to 0. So that we look at sigma 1, 1 and sigma 2, 2. Well, I have 1 and I have 1. So in this case, sigma 1, 1 is equal to sigma 2, 2. So therefore, this state is actually hydrostatic because again, sigma 1, 1 is equal to sigma 2, 2. Come down to the next one. Well, 0 and 0 for my shear. So I can say that, okay, tau is equal to 0. So it's going to be principal or hydrostatic. And I look at the sigma 1, 1 and sigma 2, 2. Well, in this case, they're both 3. So sigma 1, 1 is equal to sigma 2, 2. Therefore, this is a hydrostatic stress state. All right, and finally, last one. Again, I look at my taus. I have 0 and 0, so tau, of course, is going to be 0. So this is going to be principal or hydrostatic. So I look at sigma 1, 1, sigma 1, 2. I got -1 and -1. So just like before, I have my sigma 1, 1 is equal to my sigma 2, 2. Therefore, this is also a hydrostatic stress state. So it's kind of funny how it went down from general, principal, hydrostatic, hydrostatic. I know that if this was a midterm scenario, this would freak a lot of students out, having the answers kind of perfectly in line like that. But yeah, that's question 1. Again, not too bad at all. It's just testing your knowledge on general, principal, and hydrostatic stress. I'm going to say stress so many times during this, I can just feel it. A hydrostatic stress state. So let's move on to question 2. So question 2 says, for the stress state shown below, and assuming the vector n is inclined 45 degrees with the basis vectors, determine A, the components of the unit vector n, B, the traction vector, C, the normal stress, and finally D, the shear stress. So this is kind of an all-in-one question where everything that we talked about in the theory is kind of being asked for besides the principal stuff. But don't worry, we'll get to that a little bit later. So if we look at this question, we're given this stress state, and I'm really trying not to say stress state, stress state. The question becomes, okay, what is my sigma matrix? Because if we have the sigma matrix, then everything is pretty easy. But the problem is we don't really know what exactly it is. So we're going to come down here and we're going to say, okay, well, remember, this is going to be two-dimensional. So my sigma is going to have 4 components with basically 3 unknowns because we know that it's a symmetric matrix. So if we know sigma 1, 2, we also know sigma 2, 1. So the first one is the sigma 1, 1. So this is going to be in the horizontal direction. And if we look at our figure, the stress in the horizontal direction is just 1. So we come down here, all right, sigma 1, 1, that's just equal to 1. Well, how about the vertical direction? So if I draw a vertical line, I can see that in the vertical direction, my state of stress is 3. So I'm going to write down 3. And then finally, in the shear direction, so I'm just going to highlight my 2 shear directions. So there we go. We see that it's equal to 2. And we also know that the matrix is going to be symmetric, so we know that this one down here must also be 2. So one thing the quiz doesn't tell you, but I do want to tell you is kind of a secret. The arrows make a difference. So you see how in this case, my 2 normal stresses, sigma 1, 1, and sigma 2, 2, they point away from the block. And the quiz doesn't tell you this, but what happens if they're pointing towards the block? Well, then we have to keep in mind that that 1, if the arrows were pointing towards the block, that would actually be -1. So that's kind of a little trick to remember when we were thinking about the midterm and the final. In here, it was really nice because they gave you all the positive directions, but there is a case, and I kind of erased a little bit here. There is a case where they could switch it up, and if they switch up the arrows, you have to remember that. That'll make sure that there's a negative sign, so that's something to remember. So now that we have sigma, the question is, all right, well, what is n? Well, they said that n was 45 degrees from the basis vectors. So n is simply going to be cosine of 45 and then comma sine of 45. So once we throw that in, that's easy enough. We say, okay, well then our n, oops, I don't know why I put equal sign. All right, we can say that n is equal to 1 over root 2, comma, 1 over root 2. So now I have my stress tensor, my stress matrix, and I have the normal vector to my cutting plane. Oh, what does the cutting plane mean, Clayton? Well, basically, I cut this plane right in half by 45 degrees, and now I'm trying to find my new stresses. So I'm going to come down here and say, okay, what was the first thing that asked for? Well, it said the components of the unit vector n. Oh, easy. I just figured it out. So I look here, I got n is equal to 1 over root 2, 1 over root 2. But I'm going to make a note here because, again, it could be this easy to find n, but there's something that we're always going to have to remember. N needs to be normalized. So normalized, I'll just write that down. And don't forget this. If you guys forget to normalize n, it will lead to the wrong answer later on. Luckily for us, 1 over root 2 squared plus 1 over root 2 squared is equal to 1, so therefore this is already normalized. However, there can definitely be a scenario where it's not normalized. So that's kind of the first part of the question, not too bad. Now we get to part B. It says, what is the traction vector? So I'm going to just come down a bit. Well, we remember the formula for the traction vector, which is denoted as Tn. It's just simply our stress matrix multiplied by n. So all I have to do is come down and sub in all the values, and you guys can do it by, you can do it in your head after, or even throw it in your calculator. So I remember that sigma was simply 1, 2, and then 2, 3. So I can finish this off, something like this. And I remember that I just figured out my normal vector is equal to 1 over root 2, and then 1 over root 2. I don't know why I just about said multiplied there. That makes no sense at all. All right. So all we have to do, again, we can do mental math, or we can just throw it into our calculator. And what we find is that this traction vector Tn is equal to 2.121 and then 3.536. And I just want to make sure I got it right. I got it right. There's been a lot of times in the past where I've been inputting wrong values as I go, and then everyone gets confused. But if we look at this, this is it. This is our traction vector n. We go up. Is it just asking for the traction vector? Yes, it is. So that's not a lot of work. Once we know our stress and our normal vector, piece of cake. Just multiply them together. Nice and easy. Now part C asks for the normal stress. So this is sigma n. And remember that sigma n is going to be just a scalar value. Why is it a scalar value? Well, we're taking our traction vector Tn and we're dotting this with our normal vector. So remember, the dot product will give us a nice scalar value, and all we have to do to dot it is we take the first components of the traction vector and multiply it by the first components of our normal vector. So the first component of our traction vector is that 2.121. The first component of our normal vector, which I'll just scroll up here. Actually, I have it written right here. So I'm taking the 2.121 and I'm multiplying it with the 1 over root 2. So this is 1 over root 2. I go plus, and I go to the second component of the traction vector, which is the 3.563. So we go 3.563, or 536, see? I knew I'd start mixing them up. So let's just get rid of that. 536 multiplied by the second component of our normal vector, which if we look at our normal vector, it's the same as the first one, which is just 1 over root 2. And if I look at this equation, well, I have no unknowns. Everything's nice and easy. So therefore, I just throw that all in my calculator, and I get that sigma n is equal to 4, which is kind of funny. It's all those decimal places, fractions, but turns out to be exactly 4. But remember that this has units. This is our normal stress, so therefore we should put 4 MPa. But again, it's not too bad. It's nice and easy. I come down a little bit and say, okay, last part of the question, which is part D. I'm going to check how much room I have. Oh, I got lots of room. Perfect. So part D wants the shear stress, which is denoted as tau, which we know is equal to the norm of Tn subtracted by sigma n times n. So this one looks a little bit more scary because of those norm brackets, but it's actually not too bad. Because the thing that we're going to have to remember, and I'll switch to a different color, that this inside here, all this together, this is going to be a vector. So a vector. And then all we're doing is we're taking the norm of that vector inside. So let's forget about the norm brackets and just look at what exactly Tn minus sigma n times n is equal to. Well, we know that Tn, now let's come down here. Actually, you know what, let's do a vertical just to save some room. So let's draw a vertical, something like this. We know that Tn is equal to 2.121, and then the second component is 3.536. So again, we solved for this in part B. We already know what Tn is. And then we're subtracting sigma n times n. So this will be minus, and sigma n, well, that's just a scalar value. That's just 4. And then we multiply this into the matrix of n, which we remember is 1 over root 2, and then 1 over root. So just like that, we can end the brackets. And if we look at this, well, this is very simple. We can throw this in our calculator, but it's also not too bad to do in our head. Well, actually, let's be honest. I would I would struggle a lot if I tried to do it in my head. So you guys are a lot better equipped than I am, but that's just how it is. And what I get is this is equal to negative 1 over root 2, and then 1 over root 2. So this right here, again, is still a vector, which is what we were expecting. But now to find Tn, what I'm going to do is I'm going to find the norm of that vector. So of course the norm of Tn minus sigma n times n is equal to all the components inside of that vector squared, added together. Oops, kind of made a mess there. Squared, added together, and then square rooted. So what we're going to do is we're going to have negative 1 over root 2 squared plus the second component, which is 1 over root 2 squared. And then we're going to add them together, and then we're going to square it, or square root it, sorry. And what you get is this is equal to 1. So therefore, our tau is just going to be simply 1 MPa, because again, this is a stress, so we need to include the units. So this would just be 1 MPa. So I know that this formula looks really bad, but it's actually quite simple once we figure it out. And the key is realizing that inside of there is just a vector. Now, one last tip before we end this question is this is sigma n. You have no idea how many students will put that as sigma. Please don't do that. That sigma n, if we look down here, well, that's just 4. That's just a number. It's not the stress matrix. That's kind of the key mistake that I see a lot of students make. And that's it. That's the question. So we figured out everything that we were trying to learn this week, and there was nothing really hard about it. If we look at part B, well, that was a one-liner. We look at part C, that was a one-liner. And we look at part D, a little bit more than a one-liner because that Tn minus sigma n took a little bit to kind of figure out, but after that, it was basically a one-liner. So I hope question 2 cleared up a lot of your, I don't know what the word would be, your fright? You know, your fears, that's the word. Cleared up your fears about the stress matrix and the traction vectors, because as you guys can see, it's not too bad at all. So let's move on to question 3, where we do the exact same thing, except for a 3-dimensional stress state. All right, so question 3 says a general state of stress, sigma, is given below. And we see below that we have a 3-dimensional, or I guess a 3x3 stress matrix, which is kind of the worst thing you guys can see in this course is something 3x3, not 2x2, but it's not too bad. And the question says, find the normal stress and the shear stress. So I'm going to highlight that real quick because that's going to be very important moving forward. So we need the normal stress and we need the shear stress on a plane perpendicular to the direction u is equal to 1, 1, 1. So this u has the direction of our normal vector n, which is exactly what we want. But again, there's a trick that we're going to have to remember. So again, if we're thinking about the normal stress and the shear stress, something required in both of those equations is the traction vector, and we don't have the traction vector. So our first step, whenever finding the normal stress and the shear stress, is going to be finding that traction vector, Tn. And if we remember, Tn is equal, and I'll write this down, Tn is equal to sigma times n. And if we list, oh, wait a second, we can't even figure that out because we don't know what exactly n is. So if we look above, we're given a vector u, which is 1, 1, 1. Now here's the problem. A lot of students will use that 1, 1, 1 as n, but remember, n has to be normalized. And if we look at 1, 1, 1, that thing is not normalized whatsoever. So we're going to say, okay, well, before we do this, we're going to have to figure out what n is, which is going to be u, because it has the same direction as u, but we must normalize it. So we divide it by the norm of u. So this is going to be the vector 1, 1, 1, but we're dividing it by the norm of u, which we can easily see is just going to be root 3. So the vector itself is going to be 1 over root 3, 1 over root 3, 1 over root 3. And kind of mixed up. Oops. Making that look a little silly right there. So that's kind of the key trick. It's not hard to figure out what n is, but again, a lot of students will not normalize it, and if they don't normalize it into 1 over root 3, then they're going to have a lot of problems moving forward. So I'm going to scroll up a bit so our stress matrix is still on the screen, because from here, we can actually figure out what Tn is. So I can go Tn, which is equal to our stress multiplied by n. So again, the formula is really simple. It's just the stress matrix, which you guys are given, multiplied by n, which you are almost given. And the reason why I say almost, again, because it wasn't normalized, do not fall for that trick. It's such a nasty little trick, but I guarantee you'll get a lot of students. So this is just going to be the stress matrix, which I'm just filling in the values again. We're just given this above, so nothing's really changed. So we're going to have 0, 0.5, and then 3. I'm going to scroll up a bit. I was kind of on the bottom of the iPad, so it's a little bit challenging for me. I'm not going to lie. I write a little silly, so it's kind of hard for me to write sometimes. All right, and we multiply this by our normal vectors. So we remember that this is just going to be 1 over root 3, 1 over root 3, and finally 1 over root 3. So I'm writing this all out. You guys are probably just doing this in your head. You guys are geniuses. I'm not quite there yet. Hopefully one day I'll be able to figure it out. So what I do is I just define my stress matrix n in my calculator. I put my normal vector n in my calculator, and I throw them together to get what is the traction vector. So for the traction vector, I get the first component as 0.5774, the second component as 1.4434, and the final component as 2.0207. Now, I know you guys are probably cringing right now, saying, "Oh my God, Clayton, you can't make that look nice with some fractions or something." Well, you probably can. I'm lazy. I know I haven't said in the last couple of videos, but you guys know I'm lazy. I'm not taking the time out of my life to figure that out, because decimals work just fine. And if it turns into something nice in the end, then perfect. But if not, well, that's not my concern. All right, so finding this traction vector n, this is kind of the hardest part, because we remember that the normal stress, which is sigma n, is simply our traction vector Tn, which we found above, dotted with our normal vector n. So all we have to do is just multiply all the components. So again, I'm going to look at the first component of the traction vector, which is the 0.5774. So I'll write that down. Got 0.5774. Multiply this by the first component of our normal vector, which is the 1 over root 3. So this can be times 1 over root 3. Perfect. And then I add this to the second components multiplied by each other. So if I look at my traction vector, the second component is 1.4434 multiplied by the second component of the normal vector, which again is 1 over root 3. And as you guys will see, they're all over 1 over root 3. And we add this to the third components multiplied by each other. So the third component of the traction vector is the 2.0207. And we multiply this by the third component of the normal vector, which again is 1 over root 3. Now, if we look here, there's no vectors, anything like that. This should give us just a nice simple answer, which is exactly what we get. So once we substitute all this in, I get my normal stress to be 2.33. So 2.33 MPa. So again, this is a stress. It has actual units, which in this case are MPa. It's usually given in the question what exactly the units are. Perfect, halfway done. Last part of the question that it wanted us to ask or answer was, what is the shear stress, which we know is tau. So again, tau is equal to the norm of Tn minus sigma n. So remember, this is sigma n. This is the normal stress that we found above. This is not the stress matrix. It's sigma n multiplied by n. So I know that you guys are all prodigies. I myself, I'm not. So the first thing I like to do in this question is figure out, okay, what exactly is this vector? So I come down here and I say, okay, well, Tn minus sigma n times n. Okay, well, that's just going to be a nice big 3 by 1 matrix or vector, which is going to be 0.5774. The second component is 1.4434. So these are just the traction vectors above, or a traction vector singular. There isn't two of them. I'm hopefully not scaring you guys. So this is just our traction vector Tn, and I subtract. I guess I'll keep it up here. Our sigma n, which we found above, just right here as 2.33. So this is just a scalar number. You guys are probably so sick of me slurring my words. It probably sounds like I'm intoxicated as I go through the tutorial. And then, of course, our normal vector is just 1 over root 3 for all of them. So 1 over root 3, 1 over root 3, 1 over root 3. I can finish this off, and it's very easy to see from here, okay, yeah, this is just going to be a vector. So I come down here and I say, okay, all right, my Tn minus sigma n times n, well, this is going to be equal to, and I'll just put in brackets here, I get the values to be, pretty messy, negative 0.7689. So this is component 1, so I'm going to separate them by a comma. 0.0962. And then my final one is 0.6735. So a lot of decimal places, again, a lot of cringe, but that's okay. What kind of instructor would I be if I didn't make you guys cringe once in a while? So again, this is the vector inside of that norm bracket. So all I have to do to figure out what my shear stress is take the norm of this vector. So if I were to go, okay, well, if I'm taking the norm of Tn minus sigma n times n, well, all I'm doing is taking all the components inside of that vector, squaring them, summing them, and then square rooting them. So I'm going to have 0.7698. So that's the first component, and I'm just going to square it to the second component squared, so the 0.0962 squared. And then finally the last component, so 0.6735 squared. I'm going to finish off the top of my square root sign just like that. And again, if we look at this equation, we can see that tau, or shear stress, is just going to be a single number, which I get to be 1.03 MPa. So as you guys see, if we compare this to question 2, where it's basically going from 2D to 3D, the process, identical. Nothing changes in the process. The only thing is there's a bit more work because, of course, we have extra components. Only real trick to this question that I'm going to highlight for you guys is this right here. So remember that our n has to be, let's kind of make it like that. Remember that our n vector, our unit vector, is just that. It's a unit vector. So please make sure that it's normalized. If you guys go 1, 1, 1 all the way throughout, then everything will be wrong. So it's, again, very important to know that n is normalized. After that, then the procedure is just the same, with the only part that I consider kind of tedious is finding this vector inside of the norm sign. So again, remember that this will be a vector that we have to find out. And again, this sigma n right here, that is a scalar. That is not a matrix. So scalar. So yep, that concludes question number 3. Not too bad. Again, hopefully I got over all your fears of traction vectors, normal stresses, and shear stresses, because it's not that bad. Everything in this course just looks terrible. I don't know why. It just looks terrible, but the formulations are not too bad. So I hope this helped you guys with question 3. Let's move on to question number 4. So question 4, kind of a bitch, because it's, again, one of those proofy type questions. As you know, there's kind of some little tricks you guys can remember to make these easier, and we're going to use one of those in question 5. But for a proof type question where you don't know the trick, the best way is just to kind of try and solve it. And that's what I'm going to do with question 4. Might take, actually won't take too long, but we'll go through it and see how it goes. So question 4 says, the shown state of stress is characterized by the stress matrix sigma. And as we can see below, we have a 2x2 stress matrix. 2x2, not too bad. If this was 3x3, no way in hell I'd try and prove this thing. I'd let you guys try it on a midterm or something, but maybe that's a bit too mean. So the question itself says, is there a plane other than the horizontal and vertical planes that have a compressive normal stress? So what I'm going to do for these answers, I'm just going to tell you guys, yes. There are planes that have a compressive normal stress other than the vertical and the horizontal. So when I go to these true or false type questions, I'll tell you guys the answers right away, and I'm going to show you guys how exactly I'm going to prove that. Well, for this one, what I'm going to do is I'm going to just go through the formulations and try and figure out, okay, where exactly would a negative normal stress come from? So I'm given my stress matrix, sigma, and remember that we also have a normal vector, which is what we're trying to take everything to. So what I'm going to do is I'm going to make this arbitrary. So instead of values, I'm just going to put n1 and n2, and I'm going to pretend that n1 and n2 are already normalized, so everything's good to go. And what I'm going to do is I'm going to go through the question as if I was determining the normal stress. So I come down here and say, okay, well, for normal stress, I need my traction vector. So my traction vector, which is Tn, it's simply going to be my stress matrix times my normal vector. So I come down here and say, okay, well, that's not too bad so far. I know my stress matrix as 1, 2, 2, and 0. And oh, that's just going to lead me to some mistakes right there. Perfect. All right, that's better. Remember, you guys deserve nice brackets. Don't let any professor tell you guys that you don't deserve nice brackets. You guys definitely deserve nice brackets. So again, there's my stress matrix. As for my normal vector, well, remember I said, okay, well, I'm just going to assume arbitrary components, n1 and n2. Multiply these together, I get another vector, so I come down and say, okay, well, I'm going to have a vector that's going to be n1 plus 2n2. And then my second component is just going to be 2n1. So something just like this. So again, I don't know what n1 and n2 are. It's an arbitrary point. It could be infinite possibilities. I say, okay, well, that's my traction vector, Tn. Okay, well, how exactly did I find my normal stress? Well, remember that the normal stress, sigma n, is equal to my traction vector, Tn, dotted with n. I come down here, okay, Clayton, that's not too bad. Those are going to be the first components multiplied by each other. So my first component of Tn, well, that's my n1 plus 2n2. So I come down here and I go, oops, I already made a mistake. All I have to do is copy it, and I'm still making a mistake. n1 plus 2n2 multiplied by the first component of my normal vector, which is n1. So I'm going to say, okay, this is going to be n1. And then I add the two second components. So the second component of my traction vector is 2 on 1. And finally, the second component of my normal vector is going to be n2. So I say, okay, well, this is kind of messy. What happens if I try and simplify things and make it as nice as possible? Well, what you guys will see is that sigma n essentially is going to be n1 squared plus 4 n1 n2. And say, okay, well, remember, the goal of this question is to see, is there a plane that would make this negative? Well, that means that our sigma n, well, this would be less than 0. So all I have to do is try and find a case where this term right here is negative. What kind of combinations of n1 and n2 would make this negative? Now, if we look at this right away, we can conclude that yes, there are combinations of n1 and n2 that will make this negative. It's going to go to basically two scenarios, or two goals that have to be met at the same time. The first one is n1 or, and I have to put or here, n2 is negative. So one of those points have to be negative. The reason why is because the only way that this term is going to be negative, and I'll switch to green here, is if this right here is a negative value. Because of course n1 squared, well, whatever n1 is, that's always going to be a positive value. So this right here has to be the negative term. In order to make that negative, then either n1 or n2 have to be negatives. And remember, it's or. If both of them are negative, then that turns positive. So the first key one, n1 or n2, but not both, is negative. So there's kind of the first one. The second one is that, of course, for n1, n2, or I guess the absolute value of 4n1, n2, has to be greater than n1 squared. That's the second kind of key component, because even if it's negative, but n1 squared is still larger than it, well, it'll still be a positive answer. So these are my two major things, and all you guys would have to do is try and substitute values into here to try and figure it out. So what we're going to do is we're going to substitute the values that were given in the website, which are n1 is equal to -1 over root 2. And we have n2 is equal to 1 over root 2. So these points do work because, again, if I were to have them as the vector n, so I'm just going to put n right here, so you guys can see what the vector n would look like, which would be -1 over root 2, and then 1 over root 2. This is normalized, so that's a key trick. I can't just substitute any values in here. I have to have values that would lead to a nice normalized vector. And in this case, the -1 over root 2 and the 1 over root 2, they do lead to something normalized. So that's good to go. I come down here and say, okay, well, what is my sigma n? Well, if I go sigma n is equal to, well, the first one was n1 squared. I'm just going to scroll down a bit. n1 squared, well, n1 was -1 over root 2. And this is squared. And we go plus 4 n1 n2. So plus 4 n1, well, that's -1 over root 2. n2, well, that's just 1 over root 2. And if we substitute all these numbers in, so again, this equation just comes from the one right above, and I'll put a green line like this. So this just comes directly from here. If I substitute in all of those values, I get that my sigma n is equal to -1.5. And of course, this is in terms of MPa. And if I look at my n vector that I used, which is this one over here, this is not a horizontal or vertical plane. This actually is kind of an angular plane. It'll actually be a 45-degree plane. So yes, that's why I answered the question yes, because yes, there is a plane other than the horizontal and vertical planes that have a compressive normal stress. One example of which is n is equal to -1 over 2, and the second component is just simply 1 over 2. And how did I kind of look at that and prove it? Well, I just looked at the equation. I figured out, okay, how would this be negative? If there was some way where, let's say we ended up with the equation, I'll put this in green. So this is not true, but let's say that we ended up with n1 squared plus n2 squared is equal to sigma n. Well, from here we can say, oh, there's no possible way, because even if I pick both n1 and n2 as negatives, or I pick both as positives, well, then there's no way that that will ever be negative. However, in this case, we can see that, oh, it can be negative under these circumstances. So I listed the circumstances, and then I found a case that worked. So I hope that helped you guys with question number 4. I'd say that this is actually the hardest one out of the quiz. So if you guys get this one, pat yourselves on the back. You guys are experts. Good to go. Now that we're done question 4, this is also halfway done the quiz. So if you guys need a moment to stretch, grab some more popcorn, maybe grab a snack, maybe some Smarties or something. I don't know. For some reason, I'm craving Smarties, and I'm taking it out on you guys. But yeah, if you guys want another snack, now would be the time to do so, because we're going to start the second half of the quiz, which begins with question number 5 right now. All right, guys, welcome back. I hope that your snacks are nice and full. Same with your drinks. And you guys are ready for more of this fun stress matrix talk. Again, it's a long quiz. I apologize for that, but we're halfway through it, and the second half isn't as bad as the first half. So looking at question number 5, it says a bar is under a uniaxial state of stress described by the matrix sigma. And if we look at sigma down here, the stress matrix, not a lot's going on. We have a sigma 1,1 component and nothing else. So in essence, this bar is just being pulled horizontally. Nothing else is happening, no shearing, no stretching in the vertical direction. Again, just being pulled horizontally. And the question says, is the shear stresses on any plane, so there's kind of a keyword right there, any plane inside the bar always equal to 0? And in essence, remember, I'm just going to tell you guys the answer first and prove it. In essence, no. There are planes in this bar where the shear stresses are not equal to 0, for sure. And the reason why is because it's simple. The only way that the shear stresses, so I'm just going to put shear is equal to 0. So in essence, the sigma 1,2 is equal to sigma 1,3, which is equal to sigma 2,3, because this is a 3D case. All of these are equal to 0. There's only one case. And I'll switch colors here because this is going to be a very important case. This is the hydrostatic stress state. Hydrostatic. Oh, I'm getting stresses and static mixed up. That's where it comes from. Hydrostatic stress state. If it's hydrostatic, then yes, for any plane, the shear will always be 0. But it's only for that case, the hydrostatic state. So if I look up here and I go, okay, well, how was hydrostatic defined before? Well, the first one was the T in the matrix is equal to 0. So if I come up here and I say, okay, well, if I look at all my stresses, which are, my shear stresses, which are those ones, they actually are all equal to 0. So I'm going, oh, wait a second, maybe this is the hydrostatic stress state, because that checks out. Now, the second part of the hydrostatic stress state kind of criteria, again, which we covered this in question 1, is that sigma 1,1 is equal to sigma 2,2, which is equal to sigma 3,3. I come up here now, and I'm just going to erase some of the previous highlighting. If I look at those components and go, okay, well, these would be these ones right here. Well, no, sigma 1,1 does not equal sigma 2,2. So therefore, this kind of part right here, this is a big no-no. And because of that, this is not a hydrostatic stress state. This right here is a principal. So therefore, this is a principal stress state. And because of that, then we can conclude from the answer, we can conclude to the question that no, the shear stresses are not always equal to 0. They're only equal to 0 on any plane in a hydrostatic stress state, which will be question 6 kind of coming up. So this is question 5. If you guys want more information about the hydrostatic stress state and why it's always equal to 0 during that state, well, then stay tuned, because in question 6, which is coming up next, we're going to discuss exactly that. So question number 6, again, we're going to talk about basically the same thing that we're asking in question 5, except now we're going to apply it to a hydrostatic stress state. So question 6 says, assume a block is subjected to a state of stress described by the matrix sigma. And again, I said that this was hydrostatic because the first kind of rule of hydrostatic is that there's no shear. If we look at the shear components, they're all equal to 0. And the second kind of criteria was that sigma 1,1 is equal to sigma 2,2, which is equal to sigma 3,3. So if we come down here, we can say, oh, okay, yeah, sigma 1,1 is equal to sigma 2,2, which is equal to sigma 3,3, which is just simply P. So yes, this is hydrostatic, and I'm going to write this down real quick so that no one forgets that this is indeed hydrostatic. Lots of fun writing. All right, hydrostatic. And it's basically the same question as question 5 above. Is there a plane with non-zero shear stresses inside the body? And the answer for this one is no. As you guys will see, every plane in this matrix, the shear stress will be 0. Every single plane. It doesn't matter how we rotate it, anything like that. Every plane inside of this stress matrix will have 0 shear stress. And you say, Clayton, that's kind of weird. How exactly do we show that? Well, again, we're going to do the same thing that we did, I believe, in question 4, where we're going to assume a normal unit vector, and we're just going to carry on the calculations to see what exactly happens. So just like before, let's say that n is equal to n1, n2, and n3. And again, this will already be normalized, so I'll just put a little bracket here in green so that no one busts my balls. This is a normalized vector. So we're going to say that, all right, that criteria is met. So let's say, okay, let's go through here and try and figure out what the traction vector would be. So I come down here. Actually, I'll keep the sigma in there. So remember that Tn is simply just going to be sigma times n. So I come down here and say, okay, well, my sigma is kind of big. It's P, 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 and 0, 0, 0. So P, 0, 0, 0, P, 0, and then finally we have 0, 0, P. Come down here. Good to go. Then the next one, well, we're timesing this by n, which again, we just put as arbitrary n1, n2, and n3. So far, we're just substituting everything in. No problem at all. Well, what you guys will find is when we do this math, you guys will find the following, which is kind of really nice. This is one of the nicer proofs, if you guys think about it. I don't know. Every time I'm looking at that stress matrix, I just see poop for some reason. I don't know. Maybe my p's were too big or something like that. So the first component is just going to be P times N1, P, N1. The second component is going to be P times N2, and then P times N3. And you guys may be looking at this and saying, oh, wait a second, this looks kind of funny. Well, let's look at the first part right here. So I'm going to switch to green. I'm going to look at this part right here. This part, as you guys may have already guessed, because it's very obvious at this point, this part is sigma n. So again, sigma is a matrix, n's a vector. I'm going to say this is equal to the second part. Wait a second, this is actually equal to P times n. Well, I come over here and I write, okay, well, we basically had sigma n is equal to P times n, where n's a vector, sigma is a matrix, and P is just a regular value. And then right here, you guys should have all the bells and whistles going off in your head. this means that n is an eigenvector. Eigenvector. Wait a second, Clayton. Well, if n's an eigenvector, that also means that p is an eigenvalue. Is an eigenvalue. So we say, okay, well, if n's an eigenvector and p is an eigenvalue, well, let's think about what exactly that means. Well, remember that this means that the matrix is diagonal. And this means that if the matrix is diagonal, that means that, well, of course, there's going to be no shear stresses. And say, okay, well, what kind of n is an eigenvector? And if we look up top, we picked arbitrary components. That means right here that we can conclude, and this is kind of hard to kind of all line up together, that it doesn't matter what vector n you pick. No matter what vector n you pick, it'll always be an eigenvector. And if it's always going to be an eigenvector, then that means that p will be our eigenvalues and that there will always be no shear. So this is kind of why. It's realizing that that relationship that we saw below. And I forgot to kind of draw something like this right here. This is equal to p times n. So again, it's a nice straightforward proof because right away you kind of look at it and go, oh, wait a second, I've seen this equation. Oh, wait, that's an eigenvector. Yeah, son of a bitch. Something like that. I hope that's what goes off in your head. So again, kind of a nice, easy proof. You guys don't really need proofs unless I give you guys the bonus question proofs, but you guys don't like it when I do that. So I probably won't be doing that too often. So all I want you guys to take away from question 5 and question 6 is that the only way, and I'm going to say this kind of very clear. Well, actually, I'm going to try to say it very clear. I have a problem trying to speak very clear, but the only way that the shear stress is always 0 in a stress matrix, no matter the plane, is if the stress matrix is hydrostatic. Only hydrostatic stress matrices have 0 shear stresses on every plane. If it's not hydrostatic, then yes, there will be planes in which there is shear stress. So that is kind of the trick. Please remember it. It can definitely pop up in a midterm, and it's a pretty ugly trick. Most students will fail with that one. So there's kind of the hint. All right, almost done. 2 questions left, and as you guys will see, they're almost basically the same. Let's move on to question 7. All right, guys, question 7. So the last real topic of the Cauchy stress matrix, which is principal stresses and principal directions. And as I kind of already mentioned, this is just kind of a hint to saying eigenvalues and eigenvectors. So question 7, very simple, says, for the stress state below, which we have sigma as a 2-dimensional matrix, determine the principal stresses, the principal directions, so we have as P and Q, and the stress matrix sigma prime in the coordinate system B, which is equal to PQ. So basically after the coordinate transformation. And I don't know why I indented A, B, and C. I don't know. It looks pretty stupid on my part, but just forgive me for that. Just pretend you didn't see it, and let's move forward. So I'm going to highlight real quick, principal. Because just like in strains, if you guys ever see the word principal, it should always be dinging in your head, eigenvalues, eigenvectors, eigenvalues, eigenvectors, something like that. Always the same for strains, well, it's the same for stresses. So if it wants the principal stresses, well, that means that I'm going to have to find the eigenvalues of this matrix. So I'm just going to write eigenvalues. That's the key to this question. Well, how do we find eigenvalues? Well, we solve the equation, the determinant, and in this case, it's usually m. I always say m minus lambda I, but in this case, it's going to be sigma minus lambda I is equal to 0. So what we can do is we can expand this out. We're going to have 1 minus lambda. We're going to have 2, and negative 2 minus lambda. And again, I'm using just straight lines. These are not matrices lines, so this means the determinant. And of course, this is equal to 0. So I come down here, and I guess I'll put part A so you guys can somewhat keep track of what I'm trying to accomplish. So if I expand this out, I have 1 minus lambda multiplied by negative 2 minus lambda. And I subtract the other 2 components, so we got 2 multiplied by 2, and this is all equal to 0. And from there I can say, oh, wait a second, this can simplify kind of nicely. Again, you guys are probably using Mathematica, I don't blame you. It's lambda plus 3, lambda minus 2 is equal to 0. So from here, it's easy to see that my lambda, which are my eigenvalues, are equal to 2 and negative 3. So if the question's asking you for principal stresses, well, that's them right there. 2 MPa and negative 3 MPa. So what I can do is I can say, all right, well, sigma 1, 1 prime is equal to, and sigma 2, 2 prime is equal to, and I'm going to order them from smallest to largest. This is how you guys see it in your assignment, so this is how I'm going to do it. It doesn't matter which order you guys really do them in, though. So sigma 1, 1 is equal to negative 3, and again, these are stresses, so this would technically be MPAs for both of them, and sigma 2, 2 is equal to 2. So that's the first part of the question, just finding the two eigenvalues. And as you guys can see, for a quadratic equation, it's not too bad. When it gets cubic, yeah, that turns into a real shit show, but luckily for us, that's not until question 8. So for right now, we're just going to forget about it and say, okay, well, this is nice. We still have a 2 by 2. I'm going to highlight this because we're going to refer to these a little bit later on. So highlight. I'm going to come down in the next part, of course. What are the eigenvalues? So remember, for eigenvalues, we're solving the system sigma p is equal to lambda p. So our stress matrix multiplied by some vector p is equal to our eigenvalue p times that same vector. So if I were to come down here and expand this out, well, I know that my stress matrix is, well, actually, I don't know. I forgot. It's 1, 2, 2, and negative 2, something like that. Well, p, we don't know p. That's what we're trying to solve for. So we're going to give it components p1 and p2. Say, all right, we got p1 and we have p2. Finish up the nice brackets, and this is equal to our eigenvalue lambda multiplied by p. So this is actually exactly what we saw in the previous question, which is why hydrostatic stress states are so special. I'll just finish up the p1 and the p2. So from this general equation, and I say general because I didn't substitute any lambdas in yet. I know what my lambdas are. They're right there. They're negative 3 and 2, but I didn't substitute them in yet because I'm going to come down here and make my equation. So therefore, actually, I'm just going to do the first equation. P1 plus 2 P2 is equal to lambda P1. Because remember, in these eigenvector problems, there's always going to be infinite solutions. So what I like to do is I just write the first equation, or if I have 3 by 3, I write the first two equations, and I can start solving. Because if I were to solve both of the original equations, infinite solutions got a problem. So if I look at this one, I say, okay, well, let's assume that P2 is equal to 1. Again, you guys can assume whatever you want. You guys don't have to follow what I do. I'm usually wrong anyways, so it may not be a good idea to follow what I do. But what I can do is I say P2 is equal to 1. Therefore, P1 is equal to, oh, sorry. Erase this. Oh, I clicked the wrong button and made a mess. All right, so plus 2 times P2, which we're just saying is 1, is equal to lambda P1. All right. Looking good so far. Well, if I look at this, my only real unknown is going to be P1 because lambda we know. So let's come down here and say, okay, well, case number 1, let's go lambda is equal to negative 3. Well, then we got P1 plus 2 is equal to negative 3 P1. Therefore, we can conclude that P1 is going to be equal to negative 0.5. And there's our first eigenvector, because now that we know P1, and we know, well, we don't know P2, but we assumed P2. Come down here. What am I doing? I'm starting to, oh my gosh, and I can't even use the eraser afterwards. All right. We know that P, our first eigenvector, sorry for those technical difficulties. I'm starting to mess up everything. It's simply going to be P1 and P2, which we know P1 is negative 0.5, and we know P2 is equal to 1, or because we assumed it. So there's our first eigenvector. So I didn't normalize it, but the question may need you to normalize it. So that's one of the things you guys are going to have to keep in mind moving forward, is that may need to be normalized. Depends on the question, stuff like that. For me, I'm not normalizing it because I'm lazy. You guys know how to normalize, so I'm not too worried about that. So this was the first case. Remember that, of course, we have two eigenvectors, and the second, eigenvalues, and the second one is 2. So if I go to my equation now, I got P1 plus 2 is equal to 2 times P1. Well, from here, it's very easy to solve that P1 is equal to 2. Just simply 2. It sounds so funny. And I guess in this case, they want it in P and R, so this would technically be R, not P. So what I'm going to do is I'm going to say that R is equal to R1 and R2. And in this case, we know that R1 is equal to 2, and R2 is equal to 1. Oh, that sounds so weird. R1 is equal to 2, and R2 is equal to 1. It sounds like the classic switcheroo. So there's the two eigenvectors. Again, they're not normalized. However, if you guys want them normalized, just to check your answers, I will give them to you normalized. So what I get once I normalize them, which again, you guys know how to normalize things. It's nothing really special. I get P is equal to negative 0.447 and 0.894. And as you guys will see, I actually normalized them for a reason because there's something a little bit special. I don't know if it'd be special or if it's a trick or what you guys would call it, but there's kind of something funny that happens when we look at these eigenvectors. And the second one, of course, is you're going to be 0.894, and the second component is 0.447. 447. Just like that. Nice and easy, easy peasy, good to go. All right, so we're going to come down here. Or I guess not down here. We're going to answer the final part of the question, which is part C. So what C basically wants us to do is find our new stress matrix, sigma prime, after the coordinate transformation into the basis set, which is made up of P and R. And if we look at these and say, wait a second, P and R above, I know it's kind of underlined on both, these are eigenvectors. And this is going to be the key here to make this question nice and easy. These are eigenvectors. So we can say, okay, well, we remember what happens to symmetric matrices when they're transformed by eigenvectors. We remember that sigma prime is going to be equal to Q times sigma transpose. Wait, this is just going to be a diagonal matrix. Diagonal matrix. And the entries of this diagonal matrix will be the eigenvalues. So I'm going to come down here and say, all right, well, I know that sigma prime is going to be equal to, and I'm just going to put my brackets in. Basically, when you're dealing with these matrices, you're just playing a big game of fill in the blanks. So I come down here, and the first thing we say, all right, it's 2 by 2. It's going to be diagonal. So these two have to be 0 because it's going to be diagonal. And remember that we said that the diagonal components are going to be the eigenvalues. So I come up here and say, okay, wait a second, I know my eigenvalues. Well, I thought I did, but okay, there they are. We know that sigma 1, 1 and sigma 2, 2, I already have them listed, are negative 3 and 2. So I just come down here and I say, all right, well, sigma prime is just going to be negative 3, 2. Nice and easy. It's that simple. So again, not a bad question at all. Kind of asks you for principal stuff. And again, if you guys hear principal stuff, eigenvalues, eigenvectors, stuff like that. And then the final thing to also remember is that, of course, our stress matrix happens to be symmetric. So therefore, if we're doing diagonal matrices and it's symmetric, well, we know that that's just going to consist of the eigenvalues and eigenvectors. All right, so hopefully that was not too bad. 2 by 2 matrices should make you guys laugh. Piece of cake. Clayton, I don't like that. Give me a challenge. I want something hard. Well, let's move on to question 8, where it's no longer 2 by 2. So question 8 says, repeat question 7 for this new sigma. And it's funny because this sigma is actually 3 by 3. And now I'm going to tell you guys kind of the secrets going on here. We got some secrets to tell you guys. The first one is that if you're ever given a 3 by 3 on your assignment, do it in Mathematica. So much easier. The second part is if you guys are ever going to 3 by 3 in an exam and you guys can't use Mathematica, it's going to be a pretty easy assignment question. It's not going to be too bad whatsoever. However, I'm lazy. I don't want to solve for anything. I'm going to show you guys how to do this question just right in Mathematica. Nice and easy. So again, what it wants is the principal stresses and principal strains. So I'm just going to go, all right, well, part A, we want principal stresses. Principal stresses. And the key you guys have to remember, as I said in the last one, this means it wants the eigenvalues. That's essentially what it's saying. Eigenvalues of our matrix. So all we have to do is define our matrix in Mathematica, go eigenvalues of M, nice and easy. So if I wanted to, and I'll show you guys, this will look really funny, but I just want to see how this goes. I can say that M, and this is in Mathematica, is equal to squiggle brackets, and squiggle brackets, 1, 1, 0, squiggle brackets, comma, squiggle brackets, 1, 3, 0, squiggle brackets, comma, squiggle brackets, 0, 0, 4. And you guys are thinking, what the hell is this guy doing? He's officially lost his mind. And you guys are right. I have. All right. So we define our matrix M. And all we have to do is go eigenvalues and then square brackets of M. And the reason why I'm not going in depth is because the process is exactly the same as before. You guys know how to get eigenvalues of 3x3 matrices, and I just thought, you know what, the quiz is long enough. Let's use Mathematica and make this interesting because Mathematica is a viable option. And what you guys will find is that sigma 1, 1 prime, and these are what I'm just saying are the eigenvalues, sigma 2, 2 prime, and sigma 3, 3 prime are going to be equal to 0.586, 3.414, and then finally the last one just is kind of funny, it's just 4. So there's how we do it for the principal stresses. Now the second part, part B, says principal directions. So principal directions or directions, I'm not even sure how to speak anymore. You guys have already probably stopped watching because let's be honest, this is just pretty cringeworthy what I'm doing right now. So this right here, this is going to be the eigenvectors. So eigenvectors. So again, we have our matrix defined up there, nice and easy in Mathematica. I just come down here and I say, all right, well, since the matrix is defined, all I have to do is go eigenvectors of M, and they'll give them to me. So I'm going to come down here. I'll put them as in terms of P, Q, and R. So P is going to be equal to 1, 0, 0. Q is going to be equal to 0.414, comma 1, 0. And finally, R is going to be equal to negative 2.414, comma 1, comma 0. And of course, part C to wrap it up is what is the matrix sigma prime going to be? Well, sigma prime, we know it's just going to be a nice diagonal matrix because again, we're using the eigenvectors as the change of basis matrix Q. So sigma prime, not P, sigma prime is just going to be the eigenvectors in a diagonal matrix. So we have them as 0.586, and I'll write them in first. 0.586. We look at what's the second one, 3.414, 3.414, and our last one is simply just 4, and it's diagonal, so every other entry is going to be equal to 0. This concludes this nice long quiz. I hope you guys had as much fun as I did. You guys are probably running low on snacks and just a little bit depressed. Let's be honest. This quiz is long. It's not a lot of fun to do or sit and listen to. So hopefully I made it as fun as it could be. I really hope so. That's my goal with these quizzes. I want to make sure that you guys are having a good time while learning things and seeing why are these actually important in life. And of course, linear algebra by itself, that's not really important. It's kind of meaningless, but now we're giving it some meaning. So hopefully you guys can see and understand and go, okay, this is why I learned determinants and matrices and symmetric matrices and eigenvalues and eigenvectors and stuff like that. So thank you guys all so much for listening. Again, I know it was a long quiz. I apologize for that. I hope that you guys are happy and learned something from it. If I wasted your time, I'm really sorry. All right. Thank you guys so much for listening. I will see you guys in quiz number 17.